So hello, welcome to our fifth and final video in our Introduction to Radio Interferometry series. In a sense, I've already told you everything I want to say about radio interferometry. This fifth video, you can think of as something as a bonus video. And it's particularly relevant for 21 centimeter cosmology, my field of research, but I think is generally interesting. For the most part, the story that I've told you so far is an accurate representation of what goes on in a radio interferometer, but we've made quite a few pedagogical approximations to make the interferometer response a little bit more intuitive. There are lots of complicating details that we didn't mention, and as you get more and more into your research and into this field, you'll discover the importance of a lot of those details. Today's video is going to cover just one of those complicating details. So let's start by writing down our visibility equation again. So here's our mathematical definition of what an interferometer measures: a visibility at one point UV in the UV plane is very much akin to the Fourier transform of the sky, ILM, after it's been multiplied by the primary beam, ALM. What's implicit in this equation, though, is that a number of these terms have a dependence on the frequency at which you make the measurement. So radio interferometers most often don't measure at one frequency, but measure over a wide bandwidth, which has been carved into a number of frequency channels. And so you get measurements at a number of discrete frequencies. And how these various terms change with frequency is quite important. So we've already mentioned that U, or again the U vector, is the UV in the exponential of the visibility equation. U is a function of the observing wavelength. So we wrote down this definition for U a little while ago. It's the baseline vector B times sine theta, the angle between the baseline vector and the source that you're observing, divided by lambda, the wavelength of the radio waves you're measuring. And intuitively, this makes some sense. A baseline has a physical length in meters. The angular scale you probe with that baseline, or equivalently, the Fourier mode you probe with that baseline, doesn't depend just on the physical length of the baseline. It depends how many wavelengths of electromagnetic radiation you can fit into that baseline. And we said that the fact that you measure a different U mode at different wavelengths, or equivalently, different frequencies, leads to the ability to use multi-frequency synthesis and fill in the UV plane by making measurements at a lot of different wavelengths. I also mentioned that a complicating factor in multi-frequency synthesis is that other terms in this equation depend on frequency. So, I said it's implicit when we write ILM that the sky brightness is actually dependent not only on position on the sky, LNM, but on the frequency. And so when your visibilities change as a function of frequency, it can be because you're measuring a different Fourier mode U, or it can be because the sky itself has changed as a function of frequency. And in truth, it's almost always both. To make matters worse, the instrument itself has a frequency-dependent response. So the primary beam is also implicitly a function of frequency. And intuitively, this is for the same reason that the baseline vector U was a function of frequency. The primary beam is defined by the antenna. The antenna is a physical piece of metal. That physical piece of metal has a different response to different wavelengths. That the size of the antenna looks different, in a sense, to different wavelengths of light. And so all three of these frequency-dependent terms, U, I, and A, add up to a complicated frequency dependence in the observed visibilities V. I said this is a particular issue for 21 centimeter cosmology, where we're trying to measure a strongly frequency-dependent signal, a very, very faint, but very, very structured signal as a function of frequency. And so lots and lots of little changes in the 21 centimeter signal from frequency to frequency to frequency. That's there in I. But if we observe frequency dependence in our visibilities, does it come from I? Does it come from U? Does it come from A? Usually, it's all three. Some terms you'll hear show up in the 21 centimeter cosmology literature include the wedge, or the foreground wedge. This terrible little piece of jargon is quite complicated in detail, but at its core, the wedge comes from the fact that you're probing different Fourier modes as a function of frequency with your interferometer. Quite often, you'll also hear about the band pass, or the process of band pass calibration, and fundamentally that means determining how the instrument evolves as a function of frequency. Often the primary beam is normalized so that it peaks at 1 at every single frequency. It has some shape dependence versus frequency, but the normalization of that peak is pulled out into a different frequency dependent term we call the band pass. And figuring out what the band pass is a major challenge for 21 centimeter cosmology. Not just because it's a function of frequency, but it can vary from antenna to antenna. The primary beam, each antenna could possibly have a different one. And physically, because the construction of each antenna is always a little bit different, each beam will be a little bit different. So you have antenna to antenna variation in A. But you can also have temporal variation in A. The electronics in the antenna that process the signal heat up, cool down, experience changes as a function of time that lead to the bandpass changing as a function of time. One last piece of jargon I want to introduce is the word chromaticity, or chromatic. And this has crept into the literature as sort of an analogy with optical telescopes, where you worry about chromatic aberration, the fact that different wavelengths of light have slightly different paths through the telescope optics. And so you'll often hear of an interferometer referred to as a chromatic instrument, or having a chromatic response, or having to correct for the chromaticity of the instrument. Fundamentally, it means things change as a function of wavelength. And the optical wavelength and color are interchangeable, and so we use similar language here. So that wraps up what I wanted to say about frequency dependence and chromaticity. As I mentioned at the beginning, there's lots and lots of other complications to the picture that we've developed here in these videos, but hopefully you found these informative, and I wish you luck in your research as you move forward.